I will present a paper made written by Professor Litano and the other colleagues Fargione, Giudice and Pataneo of the University of Catania. I may not one of the authors, but I can present it if you download this because we work together in the same field of analysis by analysis of fatigue by thermal techniques. The object of the study is it's possible of the energy release in the material subject to load application and fatigue testing. In particular, this is the traditional trend of the temperature when a specimen is subjected to a cycling loading. There is a first phase, is called phase A, in which there is a increase of temperature. The second one, very long, the most part of the life of the specimen is at almost constant temperature. Normally is called stabilization temperature. And then there is the third one that is related to the crack. And is very rapid and with a very high increase of temperature. Normally, this is the curve that is used by many laboratories. In the 80s, we were one of the pioneers in this world with research also. And we focused our attention in this part to correlate this part to the fatigue limit and correlating this rectangle to the fatigue life. And in this paper, the author start to work to correlate this part B, this phase B, to the damping energy of the specimen, and finally to correlate the final part, then the phase C, with the crack area and the increase of the crack area. There is a lot of relation linked to the work applied to a specimen that is shared in a part of Q, that is the heat and the variation of internal energy. And considering the phase B, in which the temperatures can be considered constant, and in volume and time, we can consider that it's possible to have some simplification. This is normally the Q is the head for cycle and for unit of volume, and this is multiplying for the frequency, and the volume is in 3 parts linked to the conduction, convection, and radiation. But low temperature, only the second one is the second one is predominant with respect to the other that are negligible. And at the end, it's possible to give any simplification and correlate the damping, plastic damping, which is the ratio between the energy loss and the energy applied to the specimen, directly with the temperature, and finally considering some parameter of the test, then considering the number of cycle on the phase B and the energy constant, then constant is value E1, is possible then correlate the damping, the plastic damping to the parameter linked to the dimension, frequency, applied stress, and temperature. And then it's possible to have a direct control of the damping by controlling only this difference of temperature that is the most important parameter in this case. On the other hand, the third part of the curve is related to the increase of the temperature and the increase of the area of crack. The value of the temperature in this part, could be linked to this relation. Then is linked to the variation of temperature until the stabilization, and finally by the number of cycles of the test. One hypothesis supported by the experimental test correlated the area of the crack to the temperature because they have almost the same behavior. The behavior for both is very similar, and then it's possible to correlate the crack area with the temperature, and then with the difference of stress and square stress, and finally to correlate the rate of increasing crack to the difference of stress. Sorry, I read briefly on this part because it's possible at the end founding some of the parameters necessary to this relation to give a law similar to the Paris law that is correlated the increase of area cracking, the area of the crack to the difference of temperature square. The experiment was conducted by on stainless steel specimen. This is the figure of the specimen using a stepped procedure. On the same specimen are applied different value of stress for a constant number of cycles. There is different train of cycle, and I remember 3,000 cycles with a loading ratio of 0.1, then in tensile testing. And many parameters are analyzed. The point of the surface specimen with higher temperature, the value of the stationary temperature in the stabilization of the phase B, the number of cycles corresponding to the difference between the failure and the final part of the stabilization, the number of cycles which determine the breakdown of the specimen, and obviously the temperature in all the phases, and maybe in the phase C. These are the results that confirm the normal trend of the temperature, very rapid rise, and then long stabilization. And this is the final part. So I have to explain that the temperature started always from 0, but normally we have the first step, the second step, and the third one, and so on. They are in the segments. The table 2 shows the results in terms of damping, in terms of difference of temperature, and in terms of number of cycles to be failed. This is the result of the test showing how is very easy to find the fatigue limit as a function of the stress applied on the base of the stabilization temperature. And these are the results of the test for the final part. Particularly, I have to put the conclusion rapidly, explaining the stress to rupture, the fatigue limit of the specimen, and particularly the area of the figure that represents is proportional to the energy that is expended for the specimen. The area for the total area for the figure under the curve, and the area of the third part, the part C, that is related to the crack growing, and finally the ratio between them. This summarizes the result obtained. In the same figure there are the stress, the number of cycles, the green curve that you represent on the base of the parameter phi, then the area under the curve temperature, a representation of the Euler curve, the fatigue curve. And on the other hand, there is the deformation, the strain, and the damping, the plastic damping that is very high. The strain is in the plastic zone, you see more than 90%. The Euler curve was made loading ratio 0.1, frequency 10 Hz, and the result supported by other information by the literature. In conclusion, the thermographic technique has been applied to the specimen to evaluate the relative damping during the plastic phase, the beginning of the crack formation during the fatigue test, how the crack advances. Although the results need further confirmation, they are consistent with results found in the past years by the operating on various steel, and they have never been analyzed yet from the point of view, considering the third part of the course. We have worked for a long time, more than 30 years, about the first part of the results are linked to the plastic energy, to the point can be determined where the process of the local microcrystallization starts, and finally it's possible to estimate the increase of the crack area. Thank you very much for your attention.